This is Brad, and welcome back to the Analog Universe. As promised, today we're going to talk about the world's biggest spelling error. The world's most famous equation. Yeah, I'm claiming that it's possible Einstein may have misspelled his equation. That he got the math right, but maybe he didn't spell it correctly. So what do I mean by that? So let's start off then with the equation itself. E equals mc squared. E is the energy, m stands for mass, and c squared is the square of the speed of light. So what the equation is saying is that you can turn mass into energy, and if you do that, the energy that a particular mass has is equal to the mass of the object times the speed of light squared. That's how much energy mass has. Okay, that's Einstein's claim. But let's look at the question I had when I first learned about Einstein's theory of relativity and E equals mc squared. What does the speed of light have to do with the energy of a mass? Okay, great question. But what's the answer? Well, you can go online and do a search for that question. And you'll find a myriad of answers to that, all kinds of different answers. None of them particularly satisfying to me, but the main point is nobody's in agreement on it. 100 years of searching and there's no general agreement on what the speed of light has to do with the energy of a mass. Okay, kind of confusing. So I asked my advisor on these things about this. What do you think about the fact that after 100 years, nobody really can come up with a really consistent answer about why you need to multiply the mass times the speed of light to get the energy of an object? Phoebo doesn't like that. So what would the answer to this be in an analog universe? Again, it seems very obvious that Einstein got the math right, but this is one of the recurring questions we keep coming back to in this channel is, could this be an example of the Ptolemaic fallacy? So in an analog universe, you've got light traveling through some kind of interstellar medium in waves. So let's take a closer look into waves themselves. So we've got a speedboat going through water, and it's giving off waves. There's waves that go out from the side of the boat, but there's also waves going out from the bow of the boat. Now, as that boat begins to accelerate, the waves are bunching up closer and closer and closer to the bow of the boat as the boat goes faster and faster. So instead of these long waves you've got going out from the side of the boat, you've got these short little waves bunched up in front of the boat, and those are putting pressure against the boat as it tries to accelerate. So as it gets closer and closer to the speed of those waves, you have more and more waves bunched up in front of the boat, exerting more and more pressure, and it takes more and more energy to accelerate the boat past those bow waves. Once you do, boat captains will tell you the boat starts planing, or it'll rise above those bow waves, and then you can go faster and faster. And there's less pressure against the bow of the boat, and it takes less energy to accelerate the boat after that. Okay, so here's a memory I have, probably a good 25 years ago. I don't even know when it was, but my mother, who sadly isn't here to ask about this anymore, but I remember she told me She took a trip. It was a tour around Europe. I think the Greek Isles, and then she came back to the United States. And on the way back, this tour company had booked the people back on the Concorde, the supersonic transport, the SST that flew across the Atlantic at supersonic speeds. Here's what I remember my mom telling me. Now, this is an old memory, but this is what I remember, is that shortly before they crossed the sound barrier, the captain came on the intercom and said, "We're about to cross the sound barrier." And she said, you could actually feel the plane cross the sound barrier because it kind of sped up a little bit, like a boat cresting the bow wave and speeding up as it got over the bow wave. The same thing appeared to be happening on this SST that she was riding in. Okay, that's a really old memory, and I'm not going to swear to it, but are there any Air Force pilots out there who have flown supersonic jets? If so, tell us what happens right as you cross that sound barrier. Is my memory correct? Write a note below. So, if that's what happens when boats crest their bow wave, and when jet planes go supersonic and pass what's known as their shock wave that's in front of them, it seems to be a phenomenon common to waves. So we've talked about what would happen in an analog universe as a spaceship nears the speed of light. But let's now talk about what would happen as a spaceship exceeds the speed of light, crosses that light barrier, and goes super radiant. Okay, I made that word up. See, light is electromagnetic radiation. So if crossing the sound barrier means going supersonic, then maybe crossing the light barrier might be called super. Okay, Phoebo, I'll stick to real words. At any rate, in an analog universe, theoretically, there's nothing that would stop you from going faster than the speed of light. Now, there are other problems to that, so science fiction authors don't get too excited about this, but we'll get to those closer to the end of this episode. Okay, so let's look again at light waves. Light waves go fast. They go real, real fast. If you were traveling at light speed from here to the moon, in 1 second, you'd be almost 3/4 of the way to the moon. With such incredibly fast speeds, then, the shock wave that would build up in front of a massive object as it nears the speed of light would be presumably incredibly intense. And so, just as a boat cresting its bow wave or a plane, surpassing its shock wave and going supersonic, as a massive object started to approach the speed of light, that shock wave in front of it would exert more and more pressure on that object, requiring more and more energy for that object to actually exceed the speed of light. And so, presumably, the amount of energy it would take to accelerate a massive object past the speed of light would be huge. So obviously, I think Einstein got the math right in his famous equation, E equals mc squared. But in the analog universe, what you're measuring is not the energy of the object. Again, the energy of the object equals the mass times the speed of light squared. In the analog universe, what you would be measuring is the amount of energy it would take to accelerate a mass past the speed of light. So the equation wouldn't be E equals mc squared, it would be E equals mv squared, with v being the velocity it takes to accelerate an object past the speed of light. Again, Einstein's equation describes the amount of energy inherent in a given amount of matter. In the analog universe, the equation describes how much energy it takes to accelerate that mass past the speed of light. What would it look like for something to exceed the speed of light then? Okay, so with a boat, if you look at a boat's wake, the first wave is the largest wave, and then subsequent waves get smaller and smaller. I remember for 6 months I lived in Redding, California when I was in 4th grade. And back then, the Air Force would do tests with their supersonic planes out in the desert east of Redding. And on occasion, we would hear sonic booms. It doesn't happen anymore. You can't fly supersonic above land, but back then, I remember hearing sonic booms. Am I crazy? If you used to live in Redding back in the 60s, write a note below. Did you hear sonic booms? But anyway. And those booms, you heard a loud boom, which would then peter off slower and slower. Just the same as often you'll hear a crack of lightning with a loud boom that you know, the sound then fades out lower and lower. Okay, so that's what you would expect if something crossed the light barrier. Again, we're talking about light is the medium, so you would expect a very bright light that would then fairly quickly fade off. And yeah, if you go on YouTube and you search for, old atomic tests that were above ground, that's what you see, this bright flash that then fades off. So that's what you would expect, and that's consistent with what you would expect to see with something being accelerated past the speed of light in an analog universe. Okay, so in that analog universe, what's happening in a nuclear explosion? In Einstein's universe, you're changing mass into energy. In the analog universe, perhaps you're just accelerating that mass past the speed of light. The phenomenon we see of the nuclear explosion would be consistent with that. The amount of energy that's liberated when these nuclear forces explode in the atoms, within the nuclear fuel, that amount of energy equals the mass of that nuclear fuel times the square of the speed of light, or again, E equals mv squared. So again, in an analog universe, mass could be accelerated past the speed of light. However, the amount of energy required to do that, just think about it for a second. I think the average weight of a car is about 4,300 pounds. So if you build a spaceship that weighs about as much as a car, and then you wanted to accelerate that spaceship past the speed of light, you would take the speed of light, multiply that huge number times itself, then multiply that times 4,300 pounds. The amount of energy we're talking about is just huge. Plus, you have that much pressure on an object. Is any object going to be able to withstand those kind of pressures as it crosses the light barrier or the speed of light? I don't know. I don't see it happening anytime soon, but is it possible that we are accelerating atoms, or more likely subatomic particles, past the speed of light in a nuclear blast? I'm just asking the questions. Again, we've looked in the same direction for 100 years. I'm just saying, what about this direction over here? What do you think? Write a comment below. Join us next time when we talk about the peer review funnel. See you then.